Okay, Griffin, you can take it away.
Great. Um, let me- sure. All right. Okay, can everybody see my slides fine? Great. Yeah, thank you so much for the invitation and yeah, the opportunity to share some of my work with you guys. Um, I'm going to mainly talk about my current project at MIT. Um, which is trying to emulate these small scale subgrid processes in the latest version of the System for Atmospheric model, SAM. This is, this is a lot of research, like very collaborative. It's not just me, it's my advisor here, Paul O'Gorman, um, Yanni Yaval, who was a postdoc in this group before, who started a lot of this work and is now, I believe, a visiting researcher at Google Research, and Murat, who designed the SAM model that we're using in conjunction with our machine learning model. Um, I'll just say quickly about myself. Not because it's super interesting, but just more so you guys can understand where I'm coming from. I come at this actually more as my training is an atmospheric scientist. I switched over somewhat to machine learning in my PhD. Um, yeah, but for me, it's very much like I try to think of it as solving problems, as how can I apply the tool, and that's something I've tried to continue forward at UC Irvine during my time with Google, and now here at MIT. And a lot of that has been working on what have been pretty long-term problems with gCMs or general circulation models, where our global climate models are run at a fairly coarse resolution, typically 50 to 100 or even 200 kilometers horizontally. And this creates a lot of problems downstream because the things we care about in the atmosphere, think about like giant thunderstorm clusters, mesoscale convective systems, just the formation of individual clouds and precipitation, not to mention all of the atmospheric chemistry, the microphysical processes going on, are all much smaller scales than the typical resolution of a model grid box here. So that means that all of these processes here have to be parameterized or estimated. Um, and as you can imagine, this induces a ton of errors in our climate models. Um, whether that is with extreme precipitation, large tropical precipitation like the intertropical convergence zone, all a whole host of processes. And the smaller scale the process, the more likely it is that a huge error is induced into the system. And thus far, there have been two main ways of dealing with that in terms of like a traditional physical approach. Something called superparameterization, which is what I spent a lot of my PhD working around, which is the idea of taking that like giant macro model of the globe and embedding these mini models within that are two-dimensional to resolve some of these moist convective processes. Or more ambitiously, just a high resolution 3D global simulation of the Earth. And all of these, like both of these directions of work have big benefits in terms of um, better representing mesoscale convective systems, our storms, the diurnal cycle of precipitation and convection over land, which is actually very poorly represented in a lot of climate models, and extreme precipitations and our tropical precipitation patterns. But increasing the resolution of a climate model just massively increases the computational costs. And this is, both a limited resource and a resource that's not magically improving. Um, a lot of you probably know about Moore's law, the idea of the number of transistors in a chip doubles about every 2 years. which is certainly progress, but if we just relied on computational increases to power high resolution climate models, it would be well into the next century, if not much longer, that we could power these high resolution climate models at the small scales we need to accurately capture these convective processes and cloud formations. And for a lot of what, in my opinion, climate scientists want to understand, the nobody wants to wait a century for that. And that's why I think a lot in the last 5 to, at this point, if yeah, 5 to 8 years, you've seen people turning away from this traditional approach of waiting for more computational power for higher resolution to try to get around this deadlock in our climate modeling today. It was back in 2003, David Randall put out a paper calling it the cloud parameterization deadlock, basically, where we have these two groups of climate models, right? We have our core gCMs. Um, you can run them a super long time, but they don't physically resolve the key features of the atmosphere we care about. And then we have those higher scale storm resolving models, which perform much better on things that have historically been problematic in gCMs, but we can't run them the decades or centuries we need to understand the cloud climate feedbacks of the atmosphere and really understand how, with climate change, precipitation patterns will change, low clouds will change. We just don't have the time scales there with the current computational limits as constrained by Moore's law. So this is where the idea of machine learning was first, kind of shown to me, and where I first got super interested in this is the idea of trying to break this cloud parameterization deadlock by hacking into our climate models and replacing the expensive parts, the very complicated subroutines in the climate model with neural networks. The idea of this hybrid climate model. Um, and the idea is that you can try to get the best of both worlds, maintain the accuracy of this, expensive storm resolving model, but replace the expensive parts with a neural network that will work in a much cheaper fashion. And it might be quite expensive to train the neural network, but once it's coupled to the model, it should be able to run at a fraction of the computational cost. Um, And in my specific work here at MIT, as I was saying, I use the model SAM, the System for Atmospheric Modeling, which is one of several of these high resolution storm resolving models, um, building on, previous work that had been done here. And what's also different about the approach, that Paul and I do compared to a lot of there are plenty of other groups that do some version of this, the idea of a hybrid climate model. Uh, Too many to name actually, but a lot of times you get problems with the neural network not being, not understanding physical laws and giving you very unphysical predictions. Like, on the simplest sense, if you ask a neural network to predict precipitation, it could return a negative precipitation. If you ask it to predict wind, it could give you very unphysical values of wind. And there are different ways of dealing with this. During my PhD, one of the outputs of the climate model I had to predict was precipitation. So, I added in architecture constraints into my neural network to force it to predict positive precipitation. But the approach we take actually here is to, rather than predict the subgrid tendencies of the model, is to just predict the actual fluxes themselves of the model, to try to avoid this general issue of non unphysical predictions with the neural network. Um, and what we have here is a lot of data from SAM. and I should specify again, it's the latest version of SAM, the gSAM model here. And this is significant because gSAM has a realistic land component to it. Previous iterations, previous neural network work done with SAM was strictly over Aquaplanet, which is a very different animal. And we have basically output from what's similar to what's called the Diamond 2 intercomparison project, which is basically a month or 40 days to be precise of this climate model simulation. And it is quite high resolution for a climate simulation. It is about 2 kilometers horizontally in the mid latitudes, 4 kilometers in the tropics, so contrast that against a 200 kilometer or 100 kilometer global model simulation. This is quite high resolution. You're going to have a lot of detail, processes captured in the atmosphere that would not typically be captured. And this is what serves as the base of training for our neural network. And we actually do coarse grain this somewhat by a factor of 12x. So you can do the math out there. That goes from about 2 to 4 kilometers to 24 to 48 kilometers, depending on your latitude you're at. But that's still a very high resolution. That's still much higher resolution than normal. Um, and then we use this. We take the state variables within this climate model output, temperature, water, pressure information, all of it to calculate the fluxes we need to train the model. Um, and basically, what we have here is a fairly high volume training data set for this offline neural network. And we can take this and then do this column to column prediction. Um, Generally, I think the consensus is within these climate models that vertical structure is the important one to preserve. So what we'll do is we will feed the neural network these columns of this training data and have it predict the fluxes in the same column here all across the globe. And through enforcing this column to column prediction, we try to train the neural network in this real geography setup here where, again, just on the highest level, the challenges induced by this are you have things like if you're running a prediction out much longer, things like the seasonal cycle, the interactions at the coast, and you get a powerful diurnal cycle of temperature, of deep convection forming in the tropics in the mid-afternoon that you don't see with just a simpler aquaplanet. And the hope is that this setup will allow that type of prediction. Um, and to predict these subgrid processes, this or subgrid fluxes, I should say, not tendencies, subgrid tendencies or fluxes, and which is the general microphysical package here, we give the neural network a temperature column, a column with water vapor information. We tell it what the land fraction is about the column. Is it over ocean? Is it over land? Or is it on the coast? And we also feed it the surface reference pressure, which is a proxy of the terrain. Um, is it over mountain or is it over a flat land? Is it over ocean or is it over a hill, basically? As well as we also feed it the area size of the grid cell, which is going to be different in the tropics versus the mid latitudes versus the polar regions. And then we are predicting the T advective flux out, um, the non-precipitating water, the cloud ice sedimentation, these cloud microphysical tendencies, and the phase change from liquid to ice of precipitation. Um, And the hope is that we can predict these five outputs well, and that we can then couple this neural network into the architecture of the gSAM global model and run it in much the same way you could run the physical model. Um, yeah, Daniel, if you've got a question, yeah.
Yeah, sorry to cut in here.
No, no,
And
please go
this is
ahead.
a naive question, but can you just briefly explain the difference between a tendency and a flux? I'm actually not familiar with that.
Right. No, that's a good. Let me think about like on the highest level, right? So if you're running a climate model, and let's talk about t advection here. You've got your t advection at time 0 and your t advection at time 1. If you took the difference between those two, you would have your tendency, right? So in theory, zooming out, if you left a purely unconstrained neural network, you could get a if your tendency is supposed to be positive, in theory, you could get a neural network if it's not trained well, predicting a negative tendency, predicting a super positive tendency that's too big. And there are ways you could constrain that with, physical architecture, your output activation function. You could do a custom loss function that might help enforce some physical constraints. That is one way you could approach this. But what we say is we calculate the flux, which is a contribution to the tendency, and just have the neural network predict the flux, which Yanni found in the previous work to be much stabler.
Okay, so if you predict the flux, then you can reconstruct the tendency from that, and it will be more
Exactly.
reliable.
Yeah,
Okay.
it's like a lighter touch, basically. It's a lighter touch in the hybrid model architecture, kind of a do no harm philosophy, if you will. We'll improve what we can improve, and we'll avoid making anything worse, is the hope. Yeah.
If
Um,
I understand correctly, fluxes are happening at the boundaries of grid cells, right? And they're balanced. So the the tendencies are these grid cell values and fluxes are happening and at exchange between these grid cells. Is that correct? Or is it different than that?
yeah, it is, but the only thing I would say for our purposes here is you don't think about the horizontal fluxes, just the vertical fluxes within the column, which are like
Cool.
the important ones we really care about capturing. But otherwise, yeah, that's a great way to think about it. Yeah,
Gotcha.
Got it.
yeah.
Thanks.
So yeah, we predict these five flux outputs here, and just like a little bit of information here about the neural network I do. The inputs is a vector of 100 because we've got a column of temperature, a column of water vapor information, and just a tiny bit more detail here on what's going on under the hood. So those columns are size 49. The model actually has 74 levels, but what Paul had found previously, and we had a similar problem in the work I was doing when I was at Google, is neural networks really struggle when you include stratospheric information. So if we lop off the column at about 14 kilometers, um, it leads to a much more stable prediction. So you've got two of those 49 columns on the input and then five of those 49 size columns on the output. Not a particularly complicated structure here, 7 layers in total. It's densely connected. Um, I've been training at 13 epochs with a learning rate decay kicked in there on the back half, which I find is helpful. Um, I have in the past been a big fan of hyperparameter optimization, like those automated search packages you can do. I found that can really make a big difference, but this is like a pretty computationally expensive training experiment, just given the volume of data I'm giving it. So it's a little bit difficult to do that. So I've mostly done manual tuning to get a neural network that I'm mostly satisfied with. Um, One thing I don't include right now, but is very attractive to me, is the idea of vertical convolutions throughout the column of the atmosphere to help like bake in those vertical connections. Um, I saw that in some of like the recent Kaggle competitions in this sort of space that neural networks with that bake in these vertical convolution, like do 1D vertical convolutions, are actually performing quite well. That's something I think in the future I want to add into this work here. Um, and the input-output normalization is pretty important. To avoid upper, like problems predicting upper atmosphere moisture in particular, but also for any variable you stick in the input, we normalize separately each vertical level of the atmosphere. For the inputs, but for the outputs, we can normalize by the column. Um, and once we have this neural network trained up, we want to look at some test data and see if it can capture the basic signals of this gSAM data. Here's just one of the fluxes here, the temperature tendency from the phase change. And I break this up into purple, which is all information, blue, which is ocean, and green, which is land. Because again, such a big part of this work is ensuring that the physical differences between land and ocean are respected in terms of this offline training. And if you look at mean of the variable and the variance of it, it seems to capture the mean pretty well throughout the atmosphere. The variance, the dashed lines of the neural network prediction, the test data, the true test data, the solid lines, you see a bit of an under prediction, which is something I've seen in other work, but overall seems to capture the structure. Land is perhaps slight underperformance on land versus the ocean, but a little hard to say. Or if you look at the R squared skill score, um, you see across the variables like a generally learns, but this is limited to maybe this doesn't come as a surprise. Like where the variable is present, the neural network can fit the data better. Like if you think about our atmosphere, right, in the tropics, in the troposphere where you get all this like deep convection, there's a lot of moisture up into the mid latitudes for it to learn from. In the poles are a very dry place. So there's just not a lot going on there with respect to like a moisture flux. There's almost nothing in the training data for the model to learn, so the skill is quite poor. Um, And the other thing, again, I'm looking for here is a pattern difference between land and ocean here, which again is captured. And all of these things, the neural network learning to emulate land versus ocean, capture these large scale wave patterns, and at least learn a variable where the variable is active in terms of like a latitude, longitude, location. Those are things I'm like trying to accomplish here in offline mode to make a neural network that will mesh pretty seamlessly with the gSAM architecture here. And now we can ask the question, what happens when I plug in this neural network into the gSAM code base? I replace the parts of the code base where, you had physical calculation of these fluxes and instead put my neural network. The short answer is at this point we're having trouble with stability. A couple things become very apparent, just a couple hours into the simulation. You quickly see problems in polar regions like amplification of the polar jet here. The surface moisture is far too great in the tropics. Very quickly, you get this buildup of moisture that is unrealistic and causes instability downstream. And if you really hone in on dynamical variables here, You can see this is a log scale, so really look at that dark red. You see these coastal areas in the tropics, you get really unrealistic turbulent kinetic energy. And, you know, maybe from like the offline slides I showed you, you can guess what's causing these problems, right? Um, you just don't have much skill over the polar regions. So it's not a surprise to me that using the neural network over the polar regions in the climate model itself is causing some instability. Um, you could kind of see it from the R squared figure up here, but if you look at our five outputs in the global R squared, one of them really stands out as being under predicted, and that's that T advection, which I think is helping to contribute to some of those surface problems in the tropics. Uh, and just maybe the fact we're seeing problems bubble up the coastlines mean that including land fraction and surface reference pressure as a proxy for elevation are not sufficient, or at least not being weighted sufficiently in the loss function to bake in these land sea differences. So, what I'm doing right now is I'm at this kind of funky part in the work where, I train a neural network offline. I see how it performs online. I look at the problems there from the climate model simulation and try to retrain a neural network thinking about like what were those problems like. At this point I'm going back and I'm trying polar masks. I'm considering doing like a custom loss function to boost up the T advection. I'm wondering if I lock the column lower, like instead of the atmosphere column at 49, I go down to say 40. Would that lead to more stability when the climate model is run? um, and just kind of zooming out, obviously the results here are a bit disappointing at this stage in the process, but I'm hopeful, especially given how successful ML I think has been on the weather side of things. I don't know if any of you have seen any of the work done with the European Center for Medium Range Weather Forecasting with their new AI enhanced model, how well that's doing. And I do think all these successes in the weather field can translate over to the climate field with either these hybrid climate models where I'm working, the kind of end-to-end machine learning, more of like what a group like DeepMind at Google is doing. Um, Maybe even the dream of like feeding observational weather predictions into a neural network to totally avoid the biases of climate models, I think is a very attractive space. And also just in like our age of big data, a lot of satellite data, the idea of using unsupervised machine learning for this kind of data analysis and physical discovery, I think holds a lot of potential. Yeah, so that's most of what I had prepared for you guys. If you have any questions about the work or yeah, anything related, happy to talk about it, or feedback about the work as well. If you have any ideas, I'd love to hear it. Yeah, thank you all for listening.